Okay, we're back and we're going to talk about reflecting, stretching, and shrinking our absolute value graph. Hopefully, you remember yesterday working on some stretches and shrinks and reflections of the absolute value and the parabola. And how we represent a reflection, a stretch, or a shrink in a function is by multiplying. So this blank right here is multiplying. And we multiply the parameter a, okay, in the general equation where g of x is a transformation of the graph f of x. Okay, so this parameter a could be in two different places. Just like horizontal and vertical translations, we have horizontal and vertical stretches and shrinks and reflections. So I wanted to show you these before I show the examples above. A horizontal stretch or shrink happens inside the function. As you can see, my a value is inside being multiplied by the x. If it's a vertical stretch or shrink, it happens outside the function. And as you can see, my a value is on the outside of the function, so that's being multiplied by your f of x or your y. That's why it's changing vertically. I have two examples up here so you can see, and hopefully if you just think in terms of horizontal or vertical, it makes a little sense. This first example is a horizontal stretch by a factor of 2. So for stretching horizontally, you probably think, oh, probably getting wider. So if you want to go ahead and plot some of your points from your parent absolute value function, you can see, in fact, that our graph has gotten wider. If you're not sure how to tell exactly how much wider it has gotten, you can always compare original points with new points. So I might talk about this point right here, 1, 1, which is on my original, and this point right here, 2, 1. So it appears that this point 1, 1 used to be from the vertex over 1, up 1. Well, now I have this point that is still up 1, but I have to go over 2 to get there. So that's a horizontal stretch by 2. If we go look at the vertical stretch by 2, the vertical stretch by 2, we're thinking, okay, is this stretching upward or away from the x-axis? So if we do the same thing and graph or just sketch our parent graph here, we can do a similar thing that we did with the horizontal and compare an original point with a new point. So I'm going to look at that point 1, 1 again. I see I have a point right above it that's still over 1, but it's up 2 when it used to be over 1, up 1, over 1, up 2. So that's a vertical stretch by 2. Now, if you look at the equations, you might notice something that's a little confusing with your horizontal stretch. It's this 1/2 right there. The thing about horizontal stretches and shrinks is that the a value is actually the reciprocal of what's happening. So that's another little curveball you have to think of. Just like when we did horizontal translations in the original equation, it's x minus h. So you have to think opposite. Well, when we have our horizontal a value, we have to think reciprocal to think correctly about what is happening on the graph. So the reciprocal of 1/2 is indeed 2. Hence why it's a horizontal stretch by 2. Vertical stretches look exactly how you want them to. For instance, I have a 2 out front, and it's a vertical stretch by 2. So I have all this summarized in this table down here. I already talked about the top here. I made specific absolute value functions with the a parameters in there. And then we have conditions for when we are stretching, shrinking, and reflecting. So let me jump down to reflecting real quickly. If you remember from yesterday, when we put a negative outside the front of the graph, it reflected downward. That's this over here. When I put the negative a in the outside, that's a reflection over the x-axis. So that makes a difference on our absolute value graph. It will be going downward. And what that actually also does is it changes the range of the graph. This would have a range of y is less than or equal to 0 because it's below the x-axis. Now, if I would put a negative on the inside it's a reflection over the y-axis. And with a absolute value function, remember it's just a v that's symmetric over the y-axis. So if you would reflect it over the y-axis, it's going to be the same graph. So you can't really tell when a graph's been reflected over the y-axis if it's absolute value. So I point out the negatives because when we start looking at when a graph stretches or compresses, I have little inequalities that highlight the absolute value of A. Because if it's negative, we just know it's going to reflect. Then we pay attention to what its absolute value is to determine whether it's going to stretch or compress. So again, I want to focus on our horizontal, because remember, horizontal, you have to think reciprocal. So right here, it stretches when the absolute value of A is greater than 0, but less than 1. That would be a number between 0 and 1, like 1/2. Or if I took the absolute value of negative 1/3, its absolute value is positive 1/3, which is greater than 0 and less than 1. And then it says horizontal stretch by a factor of 1 over A. That means that's the reciprocal. So this would actually be a horizontal stretch by 3, even though in the function it would be a 1/3. Vice versa, you will horizontally shrink when the absolute value of A is greater than 1. So that's a number like 2 or -4, because the absolute value of -4 is 4, and you do the reciprocal of 4, which is 1/4, and you would say this is a horizontal shrink by 1/4. Okay, now I don't need to talk much about vertical because vertical is exactly how you want to think it. It's going to stretch when the A value or absolute value is greater than 1. That's a number like 4, because if you multiply something by 4, it's going to 4 times bigger. It's a vertical stretch by 4. Or if you had a -2, the absolute value is +2, which is greater than 1. So it's going to be a vertical stretch by 2. And then it will shrink if the absolute value of your number is between 0 and 1. So 1/2, -0.3, stuff like that. So smaller than 1, think of it, it's going to shrink if it's vertical. All right, I'm going to go through some examples. Any examples I do not do or do not get to tonight, we are going to finish together in class tomorrow. So here we go. We are basically identifying the reflection and or the shrink or stretch that's happening on each of these graphs. So letter A, g of x equals 1/2 times the absolute value of -x. I have two things going on now here. I have an a value of 1/2 in the front on the outside of the function. Outside means vertical. Vertical is what you want it to be. It's 1/2. If I multiply by 1/2, it's going to get smaller. That's a vertical shrink by 1/2. I have a negative on the inside. Negative on the inside is a reflection. We call it a horizontal reflection, and it's over the y-axis, because if you think about it changing horizontally, it'd flip over the y-axis. Looking at letter C, I just have one a value in here. It's 3. It's on the inside. That's horizontal, and we have to remember reciprocal, because this is actually going to be a shrink then by 1/3. Horizontal shrink by 1/3. Okay, I'm going to save B and D for tomorrow. We can also combine functions. So you can see the general forms up top there. We could have a vertical stretch shrink, or we could have a horizontal. We probably won't have both. And then if we want to think about these logically, we should always think in the order reflect, then stretch, then translate. Okay, given each equation, identify the transformations to the parent graph of the absolute value function. Then identify the vertex and domain and range. So let's just remember that the domain of every absolute value function is all real numbers. So if I, for some reason, forget to say that, that's what it is. And we're going to do this first one really quickly. I have a negative out front, which is a reflection over the x-axis. On the inside, I have x plus 6, which is my h value of -6, so I'm going left 6. And I'm going to have to finish this tomorrow, but if I move left 6, my vertex is at -6, 0. All right, see you tomorrow.